Alright, hello trig class. In this video I'm going to go over one of the homework problems that people always ask about every year. It's from the first review homework assignment. It's out of the book. This is number 32 on page 207, and it has to do with half-life. Okay, so the problem says this, and you have to read up a little bit above where the problem starts to get all this information, but the half-life of carbon-14 is 5,700 years. An archaeologist measures an amount of radioactive material in wood to be 80% of what the carbon would be in like a certain animal. Okay, and so what archaeologists can do is they can figure out how old something is. And so the question asks, could this piece of wood that the archaeologist found, in fact, let me read the question. An archaeologist unearths a piece of wood that may have come from King Nebuchadnezzar's, I don't know if I said that right, Hanging Garden of Babylon, about 600 BC. The archaeologist measures the amount of radioactive carbon in this wood and finds that it is this, 80% of the amount of carbon that would be found in like a living animal. Is it possible that the wood could be from the Hanging Garden? And then it tells us the half-life of carbon-14. Okay, so basically what we need to do is to find out how old this piece of wood would be. And if the age of the wood is around 2,600 years ago, then it could have come from that garden. If not, then it didn't. And I'm just saying that 600 BC is about 2,600 years ago. So let me just talk about the basic idea of half-life. Okay, so if we have an initial amount of material, okay, that has carbon in it. Okay, so I'm going to call A the initial amount. Every so often, every certain period of time, that amount of carbon will decay to about half as much. So what we're going to say is we're going to multiply this by 1/2, and it does that every half-life. Okay, so right here, the exponent is the number of half-lives. All right, and so this gives us the amount of material of the carbon after a certain amount of time. All right, that's the basic idea here, is that we have 1/2 to a power, and that power is the number of half-lives. Okay, so in this case, let's suppose that there was originally 100 grams or kilograms of this material. Okay, so we start with 100. All right, it's going to decay to half a certain amount of times. We're going to work on that exponent, and we would have ended up with 80 of it, because it says that we have 80% of like what it would have started with. Okay, so what goes here? It's the number of half-lives. Well, suppose T is the age of the wood. All right, the half-life of the wood is 5,700 years. So suppose the wood is like 5,700 years old. That is 1 half-life. And how did we get that? We took 5,700 and we divided it by 5,700, and that said that's 1 half-life. Okay, well, suppose that it was 10,000, or actually 11,400 years old. How many half-lives is that? Well, it's 11,400 divided by 5,700, and that equals 2 half-lives. All right, so what we're doing is we're taking the age of the material and we're dividing it by 5,700. Okay, let's say we're halfway between 11,400 and 5,700. Well, that would be 1.5 half-lives. And that's what this exponent needs to be up here on a half-life problem. So I'm going to put T over 5,700. All right, and what I need to do is solve for T. T tells me how old this stuff is. All right, so now I need to solve this equation right here for T. Okay, it's an exponential equation. So the first thing I'm going to do is divide both sides by 100. I get 0.8 equals 1/2 to the t over 5,700. All right, now this is a this is an exponential equation. And so the way we're going to solve an exponential equation is we are going to use logarithms. Okay? There's a couple different ways to approach this. One is that I could simply rewrite this thing using a log. Okay, and so I could say that we are log, and what's the base here? Well, it's 1/2. And logs are equal to exponents, and so I'd get t over 5,700, and then this would be 0.8. Okay, and then I'd have to use the change of base formula here in order to solve. Okay, the other option is I can use properties of logs. So I'm going to take this equation here, and what I'm going to do is I'm going to take the log of both sides of it. And does it matter what base I use? No, it doesn't. I'm going to take the natural log of both sides. I could still do it using like log base 10, which is just log. So it's the natural log of 0.8 equals the natural log of 1/2 raised to the t over 57. All right? Now, properties of logs say that if we have the log of something raised to something, then this power can go in front. All right? So, we're going to take this log of 0.8, natural log of 0.8. We're going to say t over 5,700 times the natural log of 1/2. And I want to solve for t. All right, so I want to get this, and this thing is all messed up. All right, so I'm trying to solve for t here. Basically, I'm going to multiply both sides by 5,700, and I'm going to divide by the natural log of 1/2. So here's what I've got. I've got t equals 5,700 times the natural log of 0.8 over the natural log of 1/2. Okay, and so now all I've got to do is get a calculator and do this. Okay, I just need to type it in. Okay, nice stuff we were doing in class. So 5,700 times the natural log of 0.8 divided by the natural log of 0.5. And let's see what the answer is. It says 1,834 years old, or about 1,835 years. All right? So that garden, whatever the heck the garden, Hanging Garden of Babylon, was from 600 BC. Well, that was 2,600 years ago. This tells us that this stuff is only 1,835 years old. Okay? And so that means that it is probably, or not, it's not from that garden. Okay? So the answer is no. It's not old enough. All right? So now I know, half-life. Is it something that we're going to use all the time this year? Because I don't want to freak you out. Well, no, it's not. But it's just something you did do in Algebra 2 that perhaps you don't remember at all or never understood that we just want to bring back a little bit. So I hope this video at least gives you some idea of how we deal with problems like this. And the main ideas are that, first of all, this sort of equation is probably the easiest way to think of half-lives. Okay? That we look at the initial amount times 1/2 raised to the number of half-lives. And how do we find the number of half-lives? Well, it's how old the thing is, or how long the thing's been going, divided by the half-life of the object. All right? Then we get some equation, and we may have to use logs to solve it. Okay? Logs come up from time to time, anytime we want to solve an exponential equation, so it's worth reviewing some of those things. All right, so I hope this video was helpful. Please leave comments, and I will see you next week.